Welcome everyone. Good morning, afternoon, or evening, depending on which time zone you're in. And welcome to the January EURASIP webinar. My name is Michael Muma. I'll be your moderator today for the Q&A. I'm from Darmstadt University of Technology and also past chair of the EURASIP Technical Area Committee on Theoretical and Methodological Trends in Signal Processing. It's my pleasure to host today's webinar and welcome you all to this exciting session. We're honored to have with us today Dr. Eva Lagunas, a distinguished expert in satellite communications and a senior member of the IEEE. Dr. Lagunas is currently a research scientist at the Interdisciplinary Center for Security, Reliability, and Trust at the University of Luxembourg, where she conducts cutting-edge research on radio resource optimization, interference, and spectrum management with a focus on non-terrestrial networks. Dr. Lagunas earned her Master's Science and PhD degrees at the UPC in Barcelona. And over the course of her career, she has held research appointments in prestigious institutions, such as the University of Pisa in Italy, or the Center for Advanced Communications at Villanova University in the USA, and CTTC in Spain. In addition to her scientific, academic, and research contributions, Dr. Lagunas has also been an active member of the European Association for Signal Processing and serving the scientific community in various capacities. Today, Dr. Lagunas will present on the topic of global connectivity via satellite communications, space radio resource management. The talk will last approximately 45 minutes, followed by a Q&A session. During the Q&A, participants are encouraged to ask questions either via the chat or orally. Please note that this webinar is being recorded, so we ask participants to be mindful of this when asking questions during the Q&A. Without further ado, please join me in warmly welcoming Dr. Eva Lagunas, and thank you all for being part of today's webinar.
Good afternoon, everyone. Thank you, Michael, for the kind introduction. Thank you, Nelly, for the invitation to give this seminar, and welcome to everyone. So today I prepared a talk on general satellite communications. So I split it. The first part of the talk would be more general on the SATCOM domain, and then the second half would be more specific to radio resource management. That's what I've been working for the last few years. Before that, I wanted to introduce a bit about where I come from. I come from Spain, but I've been living and working in Luxembourg for the last 10 years. Luxembourg is this little country in the middle of Europe between France, Germany, and Belgium. In particular, I work at the SNTs, the Interdisciplinary Center for Security, Reliability, and Trust, which belongs to the University of Luxembourg. This is our building in one of the main avenues in Luxembourg. And this is a picture of our group. And as you can see, we are a quite huge research group. It's called SIGCOM, Signal Processing for Communications. Just a few highlights about the group. So the group is led by Professor Simeon Hatzinotas. You see a bit the numbers, which of course are correlated with the size of the group. And then the research areas that we basically work on. In general, wireless communication and networking, specific focus on NTN. That's what we are going to see today. And more recently also on quantum communications. And we also have few labs where we try to, to bring the fundamental research that we do a bit closer to the final market. Good, so jumping on the topic of the session today, I'll talk about satellite communications and a bit how they complement terrestrial networks like 5G or 6G. To start with, maybe all of you are familiar with satellite communication, I guess. All of us had a little dish on the balcony to connect, maybe to get the TV from the satellite. Those systems were essentially working with geostationary satellites. Those are the ones that are quite far away, 35,000 kilometers away from the Earth. And these satellites, when you look at them from the Earth, they appear static. So they orbit at the same speed as the Earth rotation, which is quite convenient for the signal reception. That's been for many years like this, but we recently experienced a bit of a revolution on the satellite communication world. And we appeared a lot of new devices like drones, UAVs, and lower Earth orbit constellations. On the other hand, we've seen also terrestrial network evolution, 4G, 5G, and so on. And we have identified that NTN could be a good complement to these terrestrial networks, essentially because of the wide coverage that they can offer. A bit more on this old space versus new space. So we call old space what I said, right? These typical geostationary orbits. Those are very big satellites, big in size and in mass. We're talking here about few tons. This makes that this was actually very costly to manufacture and launch. And that's why basically the business was dominated by few very big players. These things are changing. The technology has evolved. We are able to build much more reduced satellite payloads, reduced in size and in mass. This also facilitated a bit the manufacturing, reducing launching cost, and it has created a lot of opportunities for new industrial players like SMEs. And the focus, of course, here is in non-geostationary orbits. I included here a couple of pictures just to show you a bit the size of what we are talking about. Is a picture of the transportation of one of these massive big geostationary satellites, from the place where they build it. They have to transport it to the launching site. And as you can see here, this requires quite significant work, and sometimes we have to put it in planes. On the other hand, with the new technologies, the new constellations, the most famous, I guess, is the SpaceX one. You can see how they are able to pack, you have here around 60 satellites in a very small area. So all that reduced a lot the cost and facilitated the deployment. Focusing on low Earth orbit satellite constellations, because essentially these are the constellations that are pushing this space revolution. You can see here a figure of the number of launched satellites versus years, and we can distinguish between geostationary and non-geostationary. And you can see here really an increase in exponential terms, especially between 2018, 2019 towards the 20s. There was a huge growth. And in fact, companies like McKinsey, that they try to predict the business, they identified that by around 2030, we'll have like 50,000 satellites orbiting above our heads. They also predicted that the satellite market will reach $40 billion by 2030. So that's why there's a lot of news, a lot of companies, a lot of industry interested on this. Why we have that interest? Well, essentially, there are two main characteristics of the space-based communication. One, we already talked about it, is the coverage. So from far away from the Earth, you are able to see a wide region of the Earth. And then also resilience. These are communications that are difficult to jam, difficult to destroy. In particular, the LEO orbit embraces the benefits of lower radiation exposure and also reduced latency. With the latency, we should be a bit careful because, of course, we still have to send the signals to space, and that takes time, the propagation time that we cannot avoid. But when we say reduce latency, it means with respect to the geostationary satellites that we had before. And then, the integration with the terrestrial networks, with the 5G, besides the ubiquitous coverage, it offers also one extra degree of freedom, which is the bandwidth that can be exploited. In this slide, I want to highlight the digital urban-rural gap because you probably know about this. Although internet access has become more affordable in all regions of the world and among all income groups, the digital divide still persists, with 2.9 billion people lacking internet access. And we don't need to go very far away. Here in Luxembourg, there are many places where the coverage is still not very good. Providing this coverage to remote areas or conflict zones, it's quite difficult for the terrestrial operators in the sense that it's too much cost. So sometimes it's not that they cannot do it. They would probably be able to deploy it, but it's not worth the investment. So in those cases, and the typical example is the maritime coverage or airplane coverage, NTN is the best solution. In this slide, I just wanted to put a bit of visuals of typical LEO constellations. I could not avoid putting Starlink that appears on the news every week. Starlink in particular, they have this the so-called Walker Delta constellation. So these are planes that are a bit tilted with respect to the equator. And this provides quite good coverage in almost all latitudes of the Earth, except the poles. As you can see here in North Pole and South Pole, you have a bit of a gap. For the OneWeb that it was recently acquired by Eutelsat, this is a bit different. You have this Walker Star constellation. These are circular orbits that go from pole to pole. And you can see it's a bit different. So on the North Pole and South Pole, you have the more satellites that are flying there. So the coverage there is quite good, and also for other areas of the Earth. Maybe it's worth to highlight the IRIS², which is the one that you have on the lower part of the slide, because the contract for this one was signed last December. So this is from the European Commission, and there's a consortium of European players that in principle will build this constellation very soon. This is just the image that they have on the websites. Not much detail so far. About the vertical domains of LEO space industry, so we can probably highlight four key markets. One is the satellite mobile backhauling, where the satellite communication links have been shown to provide very promising solution to offload congested terrestrial backhaul network. Then we have Internet of Things. You know, this is a term that we use for low power network devices that are usually like sensors. And these are usually used to monitor assets like environmental monitoring, infrastructure, transportation, logistics, and so on. And sometimes they are in quite remote location, and it's good to have wide visibility to collect the data of those IoT devices. Then we have rural enterprise broadband. This essentially is, we refer to the cruise ships, in-flight connectivity, high mobility platforms in general. And the last one is direct access. This means direct access to mobile phones, to handhelds, we call it. This already started. It's happening with simple voices and short messages, but the idea is to have at some point any service that you might have on your mobile phone via the satellite. But there are still some challenges, as we'll discuss in the coming slides. And the main challenge when you talk about space communication is the fact that you need to close the link. And that's a bit challenging because it's a huge distance between the satellite and the user terminal. Of course, this depends a lot on the type of antenna that you have at the terminal. We were talking before, when we had geosatellites, we had this dish on the balcony, everything was perfect if the dish was well pointed, because the dish is very high, it has very high directivity. The problem is that when you have to track satellites that are moving and you have to hand over very often, this type of so directive antennas might pose some challenges. So in the other extreme, we have mobile phones that they have omnidirectional antennas, but the gain is much, much lower. And that poses some trade-off, as you can see. There are some companies like AST Space Mobile that they are trying to put more antenna gain on the satellite. And this is an image of the array that they are building to put on the sky. You can see the size of such array. But in principle, with that, you will be able to connect to mobile phone simple antennas. Something in between is phase planner arrays, like the ones that you can see on this military vehicle that you can put on the rooftop, and they offer a bit much better antenna gain. We should also discuss probably which frequency we are working, because that affects a lot the link budget. Essentially, for 5G NTN communications, they have identified like two main bands. You know, in satellite, we use letters to refer to spectral bands. So we call it the S-band, the sub-6 gigahertz, which is low sensitive to weather and atmospheric impairments. This is good, but there's not a lot of bandwidth there. On the other hand, we have the K band, the so-called millimeter wave, which, you know, there's more bandwidth available, but again, the propagation and the rain fading, it's much more difficult on those bands. Some other technical challenges are related to the mobility. We discussed that from Earth standing, you see those satellites moving, and the closer they are, the faster they move. And it's not only the satellite, right? At the end, the terminal might also move, and that creates some challenges in terms of establishing the communication. The good part of it is that the satellites, in principle, they follow predictive patterns that you can exploit, for example, to compensate Doppler effects. So to close the link, you first need to compensate the Doppler, and there's many works towards this target. Another challenge is the complex ground infrastructure. So, for a satellite to send data to a user, you first need to upload the data to the sky. The devices that upload this data to the sky are called gateways. And when you had a geostationary satellite, usually you had one gateway, and that was it. As soon as you have multiple satellites, the ideal case would be that you have one gateway per satellite, so you always have access to the ground. But that, as you can imagine, is non-feasible, sometimes for political reasons, and also because it's too much expensive. So this actually motivated these inter-satellite links. That means the connection that we have between satellites that essentially creates a mesh network on the sky. And this brings the next challenge in, because once you have this mesh network, you need to develop some routing strategies, load balancing, and so on and so forth. Another technical challenge that we should mention every time that we talk about this massive LEO deployment is spectrum and the radio regulations that apply. When we started launching few satellites, it was assumed that those satellites would operate on the same bands as the GEO. That's fine. If they are few, they don't cause major interference events. But when we started launching more and more, this started to create a bit of a concern, especially to the geostationary satellite operators that were seeing just a mesh of satellites in between their satellite and the users. So it's fundamental that we should guarantee this coexistence between the different satellite systems, but also with respect to the terrestrial ones. For this, we have ITU, that's the International Telecommunication Union, that develops this radio regulation. And in particular, the articles that apply in this case, Article 22, and also this recommendation that essentially put the limits into a specific performance metric, which is this one that you have here, the equivalent power flux density. So we try to put the limits on this power flux density on the Earth and on the sky. And it's a bit difficult to calculate. That's why they provide these recommendations that everyone can calculate that. And then a bit of a standardization, right? Satellites have been operating for a long time with its own standard, which is called DBB. But of course, I guess most of the new ventures in satellite, LEO satellite communication is actually to penetrate the terrestrial market, to penetrate the 5G. And to do that, they should clearly adopt the same standard. So they should follow the 3GPP new radio standard. The non-terrestrial elements were introduced already in release 15, that was released in 2017. And from that, you saw in each release, there was a new addition discussing different elements that I'm not going to detail here. Just to mention that last year we finalized release 18. Right now, they are already working on release 19, and it's already being discussed what the release 20 will include. And one slide about sustainability, because I guess some of you already sense that might be a problem. These small satellites also come with a disadvantage, which is the fact that they have a shorter lifespan. That means that the operator should really plan to decommission them, to bring them back to Earth, when they are not used anymore. Otherwise, we'll end up with a physically very congested environment with thousands of satellites orbiting around. This would unavoidably cause some space debris, and that triggers a higher probability of satellite collision, and that might create consecutive collisions and might be a disaster. So we should be very careful with that. Also, radio astronomers are already complaining about the problematic of the light pollution. So they are already starting to complain that they could not observe other planets from the Earth because of this. Good. So that concludes a bit the first part of the talk. Second part, I'll focus a bit more on what we've been working for some time, radio resource management. Okay, so I'll start from the very basics, and then we go adding a bit more complexity. I would not detail if this is GEO or LEO. For the moment, it's a satellite that it provides some coverage to the Earth, and we have some available bandwidth that we call here BW. And yeah, if we assume we have only one satellite, one user there, we can compute the capacity as this bandwidth multiplied by the spectral efficiency of the link. And you know that the spectral efficiency is actually a function of the signal to noise ratio. Until here, everything is fine. However, as I said, yeah, the benefit of the satellite is that you see many users, that you see a wide area, right? So if we put many users, all of them operating on the same bandwidth, we have a problem. And that problem is called interference. So the interference term appears on the signal to noise ratio, and it gets down the spectral efficiency, capacity goes down. So that's a disaster. So we should do something. Possible solution that some people do sometimes is the user scheduling policy. That means that, okay, I'm still using the whole bandwidth for each user, but I'm just gonna do it in a sequential mode. So one user takes the bandwidth, next time, next user, and so on and so forth. However, here we are really talking about many users. So this approach is not really an option, because by the time that you revisit the next user, it's already too much latency for that communication link. So that's not a good way to proceed. What we usually do is we take the coverage and we split it into multi-beam footprint, like the one that you can see in the image. And then what we do, instead of using the whole bandwidth for one beam, what we do is to split this bandwidth. In this case, the example that I'm showing is splitting the bandwidth in two. And then I'm also using two polarizations, right? So you can see here the different colors refer to this different bandwidth polarization split. We call this four-color reuse, and it's essentially an interference avoidance technique. Still, you need to do a user scheduling because you still have many users inside those beams, but then it becomes more feasible. What's the problem? As I said, if we do this splitting that you see, it's very regular, right? I split the bandwidth in two, so each beam gets the same capacity. So the capacity is uniformly distributed, but the problem is that the demand is not uniform. And this is by nature of the demand, because here you can see a couple of examples. If you look at the population distribution, it's non-uniform. And also because of the mobility of the user terminals, you can see here a map with all the flights recorded in one day, and you can see there's a clear congestion here in America, in Europe, and so on and so forth, where there are places that it's actually nothing. Good. Yeah, so that brings this paradox, right? The demand in some beams is much higher than what we are offering as capacity. We call these hotspot beams. And the demand in some other beams is much lower, and we are offering them a lot of capacity, and those are called cold spots beams. The consequences are that the demand is left unmet in the hotspots, and the capacity is left unused for the cold spots. And we can really already see the problem here. The consequence for the operator are these two: a loss of the revenue that corresponds to the demand that I'm not satisfying, and a loss of the investment on the capacity that I'm actually generating, but nobody is using. This is the same, but a bit more visual. That's let's say the situation in most of the systems. You have here on the x-axis the beams, and we have here the demand in dark blue. And you can see it's non-uniform, while what we are offering, it's essentially the same for all the beams. And we have this situation. The idea would be that we come up with a design where we allocate the resources where they are needed, and we reach ideally something like that, where the bar of the offered capacity matches perfectly the demand. We call this usually demand-aware design or demand matching designs. Yeah, so the capacity to flexibly allocate onboard resources over the service coverage is becoming a must for most satellite systems. Good. How can we do that? In terms of flexibility, we usually classify satellite systems in two types, frequency flexibility or time flexibility. Frequency means maybe switching carriers or bandwidth assignment. And in time, we call this beam hopping that I will present later. You can also work with onboard antenna capabilities. So you might have satellites that have been forming networks on board, and you can play a little bit by changing the spot beam that I showed before. It was the same circle for everyone. That does not need to be the case. You can play also with that. And then in terms of optimization, we usually differentiate short term, which is basically the user scheduling, much more shorter term design versus a longer term. So frequency, time, and power are more longer term designs. Depends on the variability of the demand. Good. Yeah, since this webinar was quite short, so I decided to focus on one of these flexibility degrees of freedom, which is the time domain. And I will talk now about beam hopping. So beam hopping is one of the most flexible techniques and is shown to solve this problem of the non-uniform demand. What is beam hopping? So beam hopping basically exploits this time domain flexibility to provide all available spectrum to a selected subset of beams. And here you have an example. Let's assume you have a regular multi-spot beam pattern like the one on the left. And at a particular time instance, you decide to activate a subset of beams, which are the green ones, right? And as you can see, we can give the whole bandwidth and the same bandwidth to all of them because we are intentionally leaving some, you see, some border that they don't touch to each other. They are not adjacent. So we try to minimize the interference. What's a challenging task then here on beam hopping systems? Well, the goal that we have been trying to design was the beam illumination pattern. That means the beams that we have to activate simultaneously and for how long, right? So that's what we'll see now. To formulate this problem, basically we assume that we have a beam hopping cycle of duration th, and this is divided into multiple time slots, as you can see on the figure. Here I'm already showing an example of how we can, for example, design this beam hopping cycle. So it means red color would mean that for that period of time, I'm selecting a specific set of beams to illuminate, and each color represents another subset. This subset of beams, we call it snapshot. You can call it whatever you want. And it's basically to refer to this particular arrangement of illuminated and unilluminated beams. So here you have examples of different snapshot selection. Good. To continue with the notation, well, we make some assumptions to make things simple. We assume ideal feeder links. That means that the data is uploaded to the satellite in an ideal link, and that we don't have losses inside the payload, right? So we focus essentially on the downlink from the satellite to the user. That's the channel that we propose to use here. Very simple, again, to focus on the main design. In this case, we have the path loss. We are also putting the noise inside the channel for convenience. And then we have the gain of the receiver and the gain of the satellite. Nothing very fancy. Then the received signal is just the multiplication of this channel by the transmitted symbols. And yeah, these I already described. The goal is to find this number of T-slots that I allocate to each snapshot. Here I'll try to note you that if we consider all possible activation and deactivation, so it's like a binary variable that we have here, we will have 2 to the n number of snapshots, where n is the number of beams. And this, when n starts to be big, it starts to be quite significant. The program formulation that we propose, are many ways to do this. Here we were targeting a bit, of course, demand satisfaction, but in a fair manner. So to do that, we propose to use a max min, which is one of the typical fairness design. And we apply the max-min optimization to the ratio of the offered capacity divided by the demanded capacity. Some constraints that we have here, of course, the number of or the duration of this snapshot has to be equal to the beam hopping cycle window that we have. The second line here is just the capacity expression. It has nothing special, just maybe to highlight that we have here an interference term, because we are not actually restricting the fact that adjacent beams can be activated at the same time. We hope that the optimization is smart enough, to avoid this high interference, because rate will be low and we will not reach the demand. And then, yeah, the variable that we need to optimize is essentially an integer variable, which is the number of lots that we allocate to each snapshot. Okay, so solving this problem is difficult in general for different reasons. The first because of these large scale instances. As I said, we have many snapshots that are possible in the solution. And we also have integer in the problem. So the computational complexity, it's quite high and it has long computational time. What do we do to solve this problem? Before that, this is just an example of assuming only 4 beams. Those are all the possible snapshots. 16, in this case, still manageable, but you see usually we have 100. So that increases exponentially. And a possible solution can be like this. It means that, for example, the first and second snapshot, we are not using those, but we are using this one for 2 time slots, and so on and so forth. But you see, there are many combinations that you will need to test, and that's difficult to solve, as I was saying. Then the first thing we could do is to get rid of the integer numbers, right? To circumvent this issue, we apply some relaxations. Instead of designing the number of time slots that we allocate to each snapshot, what we can do is directly design the time that we assign to each snapshot. So we get rid a bit of the time t slot that we had there. And we basically now have just numbers that are not integer. That helps the problem. The other issue that we had was the max-min, but this we can apply a general trick that is a new auxiliary variable that we put to substitute the minimum of these different numbers, and we put it here as a constraint. And nicely, we reach a linear programming problem that in principle is easier to solve. Why I say easier? Because yes, we know that there are many different techniques like branch and bound or simplex algorithm, column generation, many things on the literature that you can use to solve a linear programming problem. But still the problem is complex. It takes too long. And essentially the problem here is that we have a huge search space. So we have a lot of snapshots. That's why before I was highlighting this 2 to the n. And since this increases exponentially, we have a bit of large scale optimization problem. What we can do to circumvent that? So here we propose to use deep learning acceleration for optimization problems. And this is not just applying machine learning solutions to the problem. And that's what I'll try to discuss here. So typical problems that we find in satellite communications and terrestrial communications are usually complex to solve. That's no secret to anyone. And you basically find different approaches in the literature. The one that we follow, optimization-based solutions. With that, you usually achieve a very accurate solution, very good solution, but the problem is that it's computationally intensive and complex procedures and so on. Some people, to circumvent that, they design heuristics that, yes, they are less complex, non-computational intensive, but sometimes the solution that you achieve has low accuracy or cannot be generalized to any type of problems. And you also need a bit of fine-tuning of the heuristics to adapt it to your problem. So can we do something else, maybe involving machine learning? So the answer is yes. The idea here is to use machine learning or deep learning to reduce the search space. The problem that we have in our optimization is that we have too many options to look at. So the idea is to accelerate the optimization by reducing the popular options And to do that, we will design a machine learning engine that selects features of the most probable solutions that will appear in the optimization. Which features? Because that's the question now, that what should we learn? So we noticed that when we were trying to solve this optimization problem, and we could do it because we had a lot of time, we could wait. So we were analyzing the solutions that we got for different demands and so on. And we actually realized that the solutions or the snapshots that were selected on the solution mostly had between 2 and 6 active number of beams. So with this information, we can actually reduce quite significantly the search space. And if we reduce the search space, we are able to speed up the optimization. That's what we did. I'll not present the details because you have the reference on the bottom of the slide if you want the details. But yeah, essentially we reach what we wanted to. Let's say we train a deep neural network with different demand instances and the solution of the optimization, and we identify for which demands was the most popular number of active beams. And then we just selected those for the actual optimization. And you can see here we are comparing CPU time in seconds for different algorithms, the branch and bound, the simplex algorithm, and the column generation. And the last column is let's say this deep learning accelerated optimization. And you see that the reduction, even if we increase the number of beams, the numbers are very low. So we achieve reduction in the complexity. I think I'm not showing the performance because in terms of performance, demand matching was more or less the same for all the algorithms. Good. Now a bit of extension that that worked very nicely, but we identify an issue. And the thing is, what happens when we have a high demand area that is composed of multiple beams? Remember that we were trying to avoid adjacent beams to be active together because we'll have a lot of interference. Well, sometimes you have high demand areas that are actually big, that they cover more than one beam. In that case, we had another paper that we designed what we call beam cluster hopping, where instead of hopping single beams, we hope clusters of beams. That was essentially the idea. What we should do here, as soon as we activate beams with the same bandwidth, is that interference appears, of course, and you have to do some interference mitigation. What we did here was to apply a simple precoding MMSC. And it was actually good because the size of the cluster was not very big. So computing the precoding matrix was not a lot of effort. Good. So yes, just some example. This is actually a demand map. The red cluster means high demand, yellow medium demand, and the blue one it's low demand. And we can see that when we design the cluster hopping following the demand, let's say, that we expect, we get a very good demand matching. Here you can see in dark is the actual demand of the beam, and in red what we are offering. And you can see that more or less we match quite well. There's a bit of a trick here because the problem is that when the demand does not match the cluster beams that we design, it's a disaster, right? So when I show this picture, everything is very nice, but you can see here I'm actually intentionally shaping the clusters based on the demand. But if I don't know that and I have a fixed cluster design, the demand matching is not happening. So this inspired the follow-up work, which was actually to have a more flexible cluster. Why we should limit the clusters to be the same size? While we should actually adapt them to the demand, right? So in this work, we were basically adapting the clusters depending on if there was high demand or not. If there's not, we just have single beams. If there's high demand that is structured, we have the same clusters, but if not, we can have a combination of them. And yeah, here you can see from the previous figure that I showed you that was a disaster in demand matching. We reached quite good demand matching. In this case, there's beams that have very high demand that we don't have enough power on the satellite to match. But for those that we could do, we do it quite well. Good. Yeah, so with this, I'm reaching the end of the presentation. These are a few conclusions. 3 bullets for the first part and 3 bullets for the second part. So I hope I convince you that the satellites can complement quite well the terrestrial infrastructure and solve what we call the coverage holes. Lower orbits have some benefits, but they also have some technical challenges that both industry and academia were trying to address. And also these open standards and interoperability will open the door to new vendors, competition, economy, and that would be very nice to see for the upcoming 5G and 6G and so on. Then regarding the design of our resource management, demand-aware design is the future. And yeah, usually we face very complex designs, power-consuming and time-consuming procedures, and some tricks that we can learn using machine learning can actually speed up the conversions of these optimization procedures. In the case that I show you today, was essentially reducing the search space of the optimization problem. Here I just drop you some selected references. In our group, yeah, we have different people working on different aspects, so I'll try to put here the more general references. Also a book that we edited a couple of years ago that provides a nice overview of non-geo satellite communications. And that's all from my side. I just want to acknowledge that this work contains some works of former and current PhD students and postdocs under my supervision, and the funding from our national agency and also from the European Space Agency. Thank you very much.
Thank you very much, Eva, for this great talk. Very interesting. I would say we now have some time for questions. So either you can put them in the chat, and then we can read them and discuss them, or you can unmute your microphone and ask the questions directly. You could also raise your hand. That would make it easier for someone to not interfere. So is there someone who has an oral question directly? Someone who would like to ask?
Always very clear, apparently.
Always very well. I'm sure there are questions. People are probably still thinking or typing in the chat. I see some applause here. So I would just begin asking some questions, but I'm sure there will be some questions from the audience. The first question that I have is about your second part, so your optimization framework. And I was wondering about the adaptability to, say, a dynamic environment. What happens if you have like real-time changes in environmental conditions or even user demands?
Yep.
What would happen then with your framework? Maybe you can comment on that.
Yes, exactly. So yeah, you notice when I was designing everything, I have the channel H that was fixed, and that, yes, you identify so that the solution of that problem is tailored to specific channel. Then it's a bit of a trade-off, right? Because if the channel changes, you probably need to, or maybe not, depends if it changes a lot or not. But if it changes a lot, you need to recalculate again the solution of the problem. So yeah, we did sometimes in some publication this trade-off, and there's no close solution. Let's say if the channel changes strongly and very often, you need to recalculate this often. It can be, this is actually faster because the time slots of the beam hopping are actually quite short, in milliseconds we are talking here. The thing is that getting the solution, it takes time. So the designer has to reach that point that is okay, that you have a good demand satisfaction and you don't need to waste a lot of time recalculating the solution. For geosatellites, the channel does not change abruptly, I would say. And if it changes, you usually have sometimes this adaptive coding and modulation. For LEO is a bit another story, but in LEO, I think you have other problems, which is handovers and so on and so forth. So you probably need to recalculate the solution more often.
We have a question in the chat regarding security aspects in satellite communications. Is there any comment
Oof.
or suggestion in this regard from your side?
There's a lot of works going on right now. I mean, satellites they are sometimes jammed, so we have intentional jamming to satellites, specific sometimes to GovSat applications and so on. There's a lot going on. So there's work trying to detect the interference, trying to address where is it coming from, trying to mitigate it by, for example, switching to another carrier, so on and so forth. There's a lot now on this quantum communication, the quantum key, and so on and so forth. But it's not really my area of expertise. But if the person who asks is interested, there's a lot available on the literature.
Mm-hmm. Okay. There's another question about the deep learning algorithm. The question is, does it refer to Adam? Also in this approach, you talk about deep learning, but is there a deep neural network? And if so, where?
Yes, it was a deep neural network. The design is, if by where is it deployed? In our works so far, or the ones I presented here, everything is designed on the ground. And then when you have the beam hopping illumination pattern, you inform the satellite, you inform the user, and everyone knows when to expect the signal. It's true that there's a lot going on having AI on space. We have actually a lab where we try to test with different chipsets because, you know, it's a lot of, then the problem is the consume power. So everything you put on the sky, it has to be very low power consumption. Also, it has to be, you know, there's radiation things on the sky, so it has to be radiation proof and so on. There's also quite some works there. Not sure if I answered what he was asking.
Mm-hmm. Nelly, if you have further follow-up questions, you can also unmute and ask directly, Eva. Okay, it seems the question was answered. Okay, another question. Is there some form of future channel prediction required, performed to enable proactive scheduling in the optimization problem?
Yes, so if we focus on the DBB standard, which was the standard that SATCOM has been using, it already includes a channel feedback. So the user measures the channel. You have to assume that satellite communications are usually frequency division. So there's different frequency for uplink and downlink. So the user has to estimate the downlink channel. And then the user retransmits the estimation to the sky and then to the gateway, and the gateway does the scheduling. So there's a way to get the CSI information, but you see it comes a bit with a delay, besides the error of the estimation. So usually the problems that we have is to have this channel estimate on time, let's say. It's a bit delayed.
Mm-hmm. So it's already delayed. And the question about predictive, is it possible to get future channel prediction? Is that even possible? Do people try this? Or?
Yes, people has worked on this. As I said, for geo satellite communications, it's much easier. Usually, I mean, depends on the frequency band and so on, but usually people try to predict the rain or the cloud events. And with that, they can predict more or less when we would have the link to go down. And then you can maybe proactively adapt the mode code to that channel, or just change to another carrier. There's a lot going on also for the LEOs on channel prediction, even demand prediction that he has not asked, but everything I said was assuming I know the demand, but this is something that you have to predict in a future step. So yeah, a lot of prediction and AI used to predict those because we have a lot of data actually. We can use it.
Okay, right now I don't see a question in the chat, so I'll just fire off one of mine about generalization. Like if you have, say, a different satellite network configuration, would you have to retrain everything, or could you basically use what you already had?
So I would say for the same constellation, so we are talking on LEOs here. So for the same constellation, you could probably reuse. So I've seen works, for example, it depends a lot on the area that you're flying. So I have one satellite that is trained for a specific area, then it moves, but another comes to the same area. You can actually transfer the learning to that satellite and it can probably exploit it somehow. It can update it with the new data that he locally gets. But yeah, there's this predictive movement of the constellation. It can be exploited, yes.
Interesting. Perhaps one more question, because I don't see anything in the chat right now. In terms of future research directions, like what are specific areas where you would say there's a significant potential for future development?
Oh, that's a huge.
A tricky one, yeah. Maybe you could pick one area that you know.
So following up on the AI that I know people is interested, we are working a lot on neuromorphic type of computing, so spiking neural networks. Why? Because we've seen those chipsets, they consume very low power. And if at some point we have to send something to space, we believe it would be a neuromorphic chipset, and this is just starting. So there's some people that claim that they are selling this already. There's people who complain that that's not exactly. So there's a lot going on. For example, Intel is developing a chipset neuromorphic. And they have a research community that you can request access as a researchers, of course. So for academic purposes, and you can actually test your designs on the chipset. That's all very interesting. Then regarding the mobility, a lot of challenges. We are working a lot on the handovers because that's something that we didn't have for the GEO, right? You connect it to a GEO satellite and the connection stays forever unless there's any problem. But as soon as you are connected to a LEO, you have to very proactively change to another satellite, and there's a bit of trade-off the same. So you would select the satellite that has the best elevation or the shortest propagation path because you have better SNR. But if you only do the change based on that, you are switching very often, let's say. And every time you switch, there's a signaling and so on and so forth. So maybe it's worth to keep the same satellite for longer so that you save on signaling, and maybe you lose a bit on the link performance, but it still makes sense. So as well, that's an area that we are exploring. Then there's a lot on the antenna design for the terminals, right? There's this the automotive market that satellites would like to enter, and the ideal case would be I put an antenna on the rooftop of my car, and then I can watch films, I can do whatever I want, right? But the cost of those antennas right now is not an option because you have to put that on millions and millions of cars. So the cost of the car will explode. Nobody will buy that just to watch a film. So there's a lot of research on actual designing of low cost, good performance. It's all an engineering problem. You don't need to be a best link, but something that it's acceptable, but with very, very reduced cost.
Okay. Is there any further question? Well, then maybe I'll have one last question. If there's no other questions, maybe you can explain a bit more about this. You mentioned the integration with 5G. What are opportunities and also challenges?
Yeah. So in terms of opportunity, I think that's a huge market, right? So satellite before, you had to buy your own dish and install it at your place. But for a satellite operator to be able to provide a service that you don't actually need to buy a specific terminal, that's a huge market that they can enter. So that's from the satellite operator perspective. For the terrestrial one, you've seen there's all these services that when you are, in the mountains, you don't have coverage, something might happen. Yeah, it's also good as a service that the terrestrial operators can provide a complement with the terrestrial. But of course, then there's a lot of diplomacy here to agree on how we use the actual waveform that was OFDM was designed for terrestrial, right? OFDM is not ideal for space communication. So the thing is that, okay, we have to use it because the mobile phones are made for that. And we have to make it work. And the problem with FDM is that they have this peak amplitude that changes a lot. They can saturate the amplifiers. It's a bit tricky how to do that. But yeah, I have confidence that at some point we'll see that. But there's a lot of discussion, not only technical, but also try to agree on a good standard.
Okay, wow. So very interesting talk. I very much enjoyed it. I'm sure everyone else did as well. So let's thank one more time, Eva. And that concludes today's webinar. Thank you very much for attending.
Thank you, everyone.